Hello everyone, I'm Tong from the Department of Applied Mathematics and Theoretical Physics in the University of Cambridge. I'm very glad to share my recent work in this very nice parity violation from home workshop. My topic today is cosmological correlators through the looking glass. This work is in collaboration with David Stefanisson in the University of Nottingham and Yuhan Zhu in the Institute of Basic Science, Korea, and is based on the following paper on arXiv. So, let's begin with a little bit of history first. As everyone attending this workshop already know, parity is a space-time transformation that flips the sign of all spatial coordinates. It was first introduced by Wigner to describe atomic physics. Parity seems to be a good symmetry in the areas of classical mechanics, Einstein gravity, and quantum electrodynamics. Until later, people found out that at even smaller scales, parity is actually badly violated. In 1956, Li and Yang was the first to propose the idea of parity violation in the weak interactions. This was soon confirmed by Wu in her experiment on the decay pattern of cobalt-60 nucleus in the same year. Later, physicists become more familiar with the notion of parity violation, and it is actually built into the fundamental structure of particle physics standard model, namely only left-handed fermions transform under the SU2 gauge group. Now if we look at the cosmic ladder, we know that parity is a good symmetry at microscopic levels, but it's actually violated at microscopic scales below 10 to the minus 20th meters or so. Then it becomes natural to ask the question, do we have parity violation at even larger scales? At the cosmological scales beyond 10 to the 20th meters, for example? Interestingly, recent studies show that it might indeed be possible that parity is violated in the form of cosmological birefringence, primordial chirogravitational waves, and galaxy trispectra. If we look backwards at the history of the universe, we find that this might not be that surprising, since the large-scale structure of the universe comes from the quantum seeds at microscopic scales at primordial eras, such as inflation. So how can we extract the information of parity violation in cosmology? Well, in cosmology, we can measure the temperature and polarization fluctuations in the CMB sky, as well as the galaxy distribution in the large-scale structures. Parity violation can then come from the form of late-time effects such as cosmic birefringence, or early-time effects such as inflation. In this primordial case, we can probe the endpoint statistics of tensor and scalar perturbations to tell parity information. For tensor modes, the intrinsic spin of the graviton is actually a pseudovector, meaning that when combined with another momentum vector, the two-point correlation function can already encode parity violation information. Thus, one can probe parity violation using the power spectra of chirogravitational waves. For scalar modes, however, there is no spin pseudovector, and one really needs to go to at least 4-point correlation level to be sensitive to parity information, because the kinematical configuration then is non-planar, and this parity violating trispectrum will be our main focus today. Such a parity violating trispectrum can be naturally generated from the inflationary evolution, illustrated by the Feynman diagram here. The vertical axis is time, and the horizontal axis represents the end of inflation. Typically, there will be some parity violating interactions going on in the inflationary bulk, and this is encoded in the 4 outgoing curvature modes, which we measure in the trispectrum. Unfortunately, there is a no-go theorem first proposed by my collaborators and I back in 2019, and recently generalized by Kabas et al. Last year. And this no-go theorem states that there can be no observable parity violation in single field slow roll inflation. To achieve a non-zero parity violating trispectrum, one really has to go beyond the vanilla single field slow roll inflation models and consider adding extra ingredients. For example, by including loop effects, breaking scale invariance, evoking non-bounce Davis vacuum, or including extra massive fields during inflation. Suppose one can do so, then there comes the question, is there any universal structure in the parity-odd sector of primordial trispectra? If there is indeed such a universal structure, can we use them to simplify our calculations? These are the two questions that we will try to answer in this remaining part of the talk. Well, if we look at the definition of the parity-odd trispectrum, we find that there is a term that goes like zeta to the minus k. Now recall, any real operator in position space is necessarily complex in momentum space. In fact, after Fourier transformation, zeta of minus k is exactly given by the Hermitian conjugate of zeta of k. And if we plug this equation back into the definition equation for the parity-odd trispectrum, we find that the parity-odd correlator has to be purely imaginary, irrespective of any dynamical details of the underlying theory. And this is a very nice coincidence with the fact that we know the world through the looking glass cannot be real. So, parity-odd correlators must be imaginary. It turns out that one can rephrase this statement and say that any real contributions in the calculation can never get into the final result of parity-odd correlators. So if we are able to identify certain real stuff in the calculation of the correlators, we can just throw them away to make our life easier. But is it possible? Let's look at the wave function of the universe, which is a nice tool that we use to compute primordial correlators. The wave function coefficients given by psi n is usually computed diagrammatically using a bunch of vertex operators, bulk to boundary propagators, and bulk to bulk propagators. And these propagators are constructed from the mode functions of various fields in the inflationary bulk, as well as appropriate combinations of the time-ordered theta functions. The vertex operators are made of a bunch of time derivatives and spatial derivatives, with appropriate powers of the scale factor in front to maintain scale invariance. And all the spatial indices must be contracted to maintain rotational invariance. And notice that in the bulk-to-bulk propagator, there are these time ordering theta functions, which leads to nested time integrals that are usually difficult to solve. So how do we compute these complicated nested integrals? Before asking this question, what one really should do is to ask another question. That is, are they really needed for the computation of the parity-odd sector of correlators? Well, we have already seen previously that the real quantities cannot enter into the final result of this parity-odd sector. What if these complicated nested integrals are purely real? Then they will be unnecessary when computing the final result. We can just discard them. The key to answer this question is by using this so-called weak rotation. Namely, we rotate the integral contour from real time direction to the imaginary time direction. This is possible due to the Bounce-Davis initial condition of the mode functions. After we perform the weak rotation, we see that both the bulk to boundary propagators and the vertex operators become purely real as a consequence of Bounce-Davis vacuum choice and scale invariance and plus unitarity. Now recall the schematic form of the wave function coefficients. we have the vertex operators, bulk-to-boundary propagators, and bulk-to-bulk propagators. Now, every one of the ingredients inside this product are purely real, except this bulk-to-bulk propagator part. Is it real too? Unfortunately, this is not true. The bulk-to-bulk propagator are in general not real after weak rotation. However, if we look back at the equations and initial conditions that define the bulk-to-bulk propagator, which is this weak rotated Klein-Gordon equation sourced by a delta function and the vanishing boundary condition at infinity. And these equations and initial conditions are purely real after weak rotation. We know that a real equation always admits a real solution. This motivates us to perform a decomposition, what we call a CF decomposition. Basically, one rewrites the bulk-to-bulk propagator, indicated by this wavy line here, into a sum of the connected propagator and a factorized propagator. This decomposition is chosen such that this connected part C is purely real after weak rotation. It's also chosen such that all the time-ordered theta functions are hidden inside this connected part, and the factorized part will be a product, a sum of products of mode functions, and cannot contain any time-ordering theta functions inside. If we plug the CF decomposition back into the perturbative solution of the wave function coefficient and expand the product of this C plus F terms, and we collect the term with all C contributions, we see that this all C piece must be purely real, because D is real, K is real, and C is also real. We will henceforth call this all C piece the maximally connected wave function psi of C, and this is purely real. The original wave function coefficient is then equals this psi C plus a bunch of factorized terms with fewer number of time ordering theta functions. Now when the integral time reaches minus infinity, the wave function generically develops a singularity called the total energy singularity, given by the sum of all the external energies. And this total energy singularity can only come from the maximally connected piece of wave function, psi C. And since we know that psi C is purely real, then all these total energy singularities inside must also be purely real. And we also showed in our paper that this total energy reality theorem can be extended to theories with bulk fields of any mass, spin, sound speed, and chemical potential. Now recall, the real stuff never get into the mirror. We know that the maximally connected wave function psi of C cannot contribute to the final parity-odd correlators. Therefore, we deduce that at tree level, the parity-odd correlators cannot have total energy singularities. They must be factorized, and because of that, they are much easier to compute than naively expected. For example, we can apply this theorem to a 4-point correlator, namely the trispectrum. In the wave function formalism, this is computed by a sum of psi 4 and a product of two psi 3s. Using this CF decomposition to rewrite the bulk-to-bulk propagator into a connected part and factorized part, we see that this maximally connected piece drops out of the final result of the parity-odd correlator, and the final result is just the sum of the factorized contributions, which we can easily compute exactly. And it turns out that all parity-odd trispectrum at tree level takes the following schematic form. For any mass, spin, and sound speed and chemical potential of the exchanged bulk field. Namely, there will be a sum of some constants, including the coupling constants and a factor of kinematics that tells you the spin information of the exchanged field, as well as two factors of hypergeometric functions telling you the dynamical information of the exchanged field. Here L and R means combinations of the left-hand side momenta and the right-hand side momenta. As we expected, there is no total energy singularities. There is only partial energy singularities corresponds to the left-hand side and the right-hand side. We also applied our exact result for the parity-odd trispectrum to this recently proposed model of low-speed collider with chemical potential, and we find that there's a perfect match with numerics. So here red line is given by our exact result, and the dotted line corresponds to numerics. One can see that in both cases the match is very well. As a summary, in this talk we leveraged on the intermittent relationship between parity and reality. Then with the help of weak rotation and the fundamental assumptions such as unitarity, scale invariance, and Bounce-Davis vacuum, we were able to show that all the total energy singularities inside the tree-level cosmological wave functions are purely real. And consequently, all parity-odd tree correlators must be factorized. There are also many future outlooks. For example, going to loop levels and try to reframe our findings in the form of Kramers-Kronig relations and try to recover the real part of the wave function given these factorized imaginary parts, and as well as how to look at our system using the Euclidean ADS perspective. And we also need a thorough classification of the total energy singularities. And that's all for my talk. Thank you very much for listening.